Hello friends, welcome back. Hearty welcome to you. In this session, let us look at one interesting example related to areas of circles. We have been given that in the adjoining figure, crescent is formed by circles which touches at the point A. Two circles are touching internally at point A. O is the center of the bigger circle. If CB is equal to 9 centimeter and ED is equal to 5 centimeter, if CB equal to 9 centimeter and ED equal to 5 centimeter, find the area of the shaded region. So we have been given that O is the center of the bigger circle. We have been given CB equal to 9 centimeter, ED equal to 5 centimeter. We have to find out the area of the shaded region. So what we will do first, we'll try to find out the approach. Area of the shaded region is nothing but equal to area of the big circle minus area of small circle. So I can write down that area of shaded region is equal to area of bigger circle, area of big circle minus area of small circle. So area of small circle. Okay, fine. We have to find out first the areas of these two figures, then we have to subtract one from the other. So but to find out the area, we need to know the radius. We don't know the radius. We don't know the radius of these two circles. So we have to find out the radii. Once we know the radii, we can easily write down that if I take the big radius is equal to capital R and the small one is small r, then what we have to find out is pi into r square minus pi into small r square. Now we have to find out what is capital R and what is small r. That is what we have to find out. For that, we will leverage whatever is given to us. We have been told that O is the center of the bigger circle and we know that CB equal to 9 centimeter and ED equal to 5 centimeter. If ED equal to 5 centimeter, then this is also equal to 5 centimeter. And now what we will do, we will take the smaller circle. We take small circle, we take this circle and we will apply the property that in a circle, if the chords are intersecting with each other, then the product of their segments is equal. That means AO into OC should be equal to DO into, let us say if this is X, OX. AO into OC is equal to DO into OX. But what is AO? AO is nothing but capital R. AO is capital R. Then what is OC? OC is nothing but R minus 9. Similarly, OE is capital R, then OD is equal to R minus 5. If OD is R minus 5, this is also equal to R minus 5. So let's write down this and try to find out the value of R so that we can also find out the value of small r. Big R is the radius of the capital R is the radius of the big circle and small r is radius of the small circle. So first what we will do, we will take the circle, small circle, and we know that product of the segments is equal. That means R into R minus 9 is equal to R minus 5 into R minus 5. Because we have been told that O is the center of the big circle. So OA equal to R, OC equal to R minus 9, OD equal to R minus 5, and if I say X, OX is also equal to R minus 5. So we'll leverage that property and we will say that R into R minus 9 is equal to R minus 5 into R minus 5. What is the logic behind this? If in a circle two chords are intersecting with each other, then the product of their segments are equal. That means R into AO into OC, I will write down AO into OC is equal to OD into, can I say OD only again, because OD, this is also equal to, let us say if this is X, then OD into OX, but that is also equal to, that's also equal to OD only, so we can say OD into OD. Now simplify this, we will have R square minus 9R is equal to R square minus 10R plus 25. Now we can cancel R square on both the sides. So when I cancel that, we will have R equal to, we'll have 10R minus 9R, that R equal to 25. So we found out capital R. Now how to find out small r? To find out the small r, what we do, we know that for the small circle, AC is diameter. AC is diameter. I can write down for small circle, AC is diameter. But AC is nothing but equal to R plus R minus 9, 2R minus 9. So 2R minus 9 is equal to 2 times of R. But what is our R value? That means 50 minus 9 is equal to 2R. R equal to 41 by 2. So once we know capital R and small r, now it becomes very easy to find out the area of the shaded region. So for that we will go back and write down area equal to pi into R square minus pi into R square minus R square. But pi we know is equal to 3.14 multiply with R square, that is 25 square, minus R, small r is nothing but 20.5 whole square. So can I simplify that and write down 3.14 into 25 plus, that is 45.5, into 25 minus 20.5, that is 4.5, which is equal to 3.14 into 91 divided by 2 into 9 divided by 2. So we can simplify that. 642.915 approximately 642.915 cm square. So the point we have to understand here is that the property what we have to remember is, in a circle, if two chords are bisecting with each other, in the small circle we are talking about, two chords are bisecting with each other, then the product of their segments are equal. Now once we know OA is capital R, OC will be R minus 9 and OD equal to R minus 5. This is also R minus 5. Since product of the segments are equal, R into R minus 9 is equal to R minus 5 into R minus 5. So we can find out capital R. Then we know that diameter of the small circle is 2R minus 9. Leveraging that, substituting capital R value as 25, we are able to find out that small r is equal to 20.5. Once we get capital and small r, it's very simple, just a little calculation, we are able to find out that area of the shaded region equal to 642.915 cm square.